Since the very first steam engine started chugging along, engineers have been chasing this one big dream: a perfectly efficient engine. One that could turn every last bit of heat into pure, useful work. But is that even possible? Well, today we're going to dive into the brilliant thought experiment that answered that question for good: the Carnot engine.
So let's just get right to it, right? Can we actually build an engine that wastes zero energy? I mean, it sounds like a straightforward problem to solve, but as we're got to find out, the laws of physics themselves have let's just say a very strong opinion on the matter.
All right, so where did this big question even come from? Our story actually starts almost 200 years ago, with one engineer on a personal quest to find the absolute limit of what any engine could do. And here he is, Sadi Carnot, way back in 1824, before the laws of thermodynamics were even fully figured out. He was obsessed with finding the maximum possible efficiency for any heat engine. And he had this incredible insight. For an engine to be perfect, every single part of its process had to be perfectly reversible. Because any irreversibility, like friction or a sudden temperature change, would just waste energy and drag down the efficiency. Okay, so reversibility, that's the secret sauce. But what does a perfectly reversible engine actually look like? To figure that out, Carnot laid down a set of super strict, almost impossible rules that this ideal engine would have to follow. So there are 4 essential conditions. First, you have the quasi-static process. Just imagine a piston moving so unbelievably slowly that the whole system is always in perfect balance. No sudden moves. Second, no dissipation. This means we're in a fantasy world with absolutely zero friction. Nothing gets lost. Third, isothermal transfer. This means whenever heat is coming in or going out, the temperature has to stay perfectly constant. And finally, adiabatic transition. When the engine's temperature does change, it has to be perfectly insulated, so not a single bit of heat can leak in or out. With those rules in place, Carnot designed a hypothetical 4-step cycle. This became the ultimate blueprint for the most efficient engine you could possibly imagine. In this diagram, this is our roadmap for the whole journey. It's a pressure volume, or PV diagram. It tracks the gas's pressure on the vertical axis and its volume along the bottom. You can see how the gas inside our engine changes as we go from point 1 to 2 to 3 to 4, and then right back to the start. The cycle has 2 isotherms. Those are the red and blue curves where the temperature is constant, and 2 adiabats, the steeper black curves where no heat is exchanged. Let's walk through it. Okay, step 1 from point 1 to 2 is called isothermal expansion. The engine touches a hot source at temperature T1, and it slowly absorbs heat. We'll call that Q1. And because the temperature is staying perfectly constant, all that heat energy has to go somewhere, right? Well, it goes directly into doing useful work, pushing a piston. Now for the next leg of the trip, from 2 to 3, we have adiabatic expansion. The engine is now totally insulated, so no heat can get in or out. The gas keeps expanding and doing work, but this time the energy for that work has to come from inside the gas itself, from its own internal energy. It's basically paying for the work by cooling itself down, from the high temperature T1 all the way to the low temperature T2. Okay, time to reset the system. From 3 to 4, we do an isothermal compression. Now the engine is touching a cold sink at temperature T2. We're actually doing work on the gas, squeezing it. And to keep its temperature from going up, the gas has to dump some heat, Q2, into that cold sink. This is the waste heat that's a part of any heat engine cycle. And the final step brings us home, from 4 back to 1. This is adiabatic compression. The engine is insulated again, we keep doing work on the gas, compressing it even more. And since no heat can escape, all that work just increases the gas's internal energy, raising its temperature from T2 all the way back up to T1. And just like that, we're right back where we started, ready for the next cycle. So we've gone through this really elegant 4-step dance. But what does it all mean? What's the big payoff here? Well, the answer is in the engine's efficiency. Okay, now this is where it gets really cool. The useful work we get out of the whole cycle is the area inside that loop on the diagram. And here's the beautiful part. You know those 2 adiabatic steps, the expansion and the compression? Well, the energy the engine puts out in one is perfectly matched by the energy we have to put back in during the other. They completely cancel each other out. That means the total net work is simply the heat we put in, Q1, minus the waste heat we had to release, Q2. So how do we define efficiency? It's just the net work you get out divided by the heat you put in. Simple enough. But here's where Carnot's genius really takes off. He proved something amazing. The ratio of the waste heat to the input heat Q2 over Q1, is exactly the same as the ratio of the absolute temperatures, T2 over T1. And when you plug that into the efficiency equation, it all boils down to this incredibly simple, powerful result. The maximum possible efficiency is 1 minus T2 over T1. That's it. Let's make this real. Imagine a power plant using steam at 300 degrees Celsius, and it's dumping its waste heat into a river at 20 Celsius. First, and this is super important, we have to use the absolute Kelvin scale. So T1 is 573 Kelvin and T2 is 293 Kelvin. We plug that in, efficiency equals 1 minus 293 divided by 573, which gives us about 0.489 or 48.9%. That is the absolute unbreakable speed limit for any engine working between those temperatures. And notice, the only way to get 100% efficiency is if T2, the cold sink, is at absolute zero, which is physically impossible.
See, this formula isn't just a neat trick for one imaginary engine. It turns out to be a fundamental law of the universe.
This all leads us to Carnot's theorem, which has two huge parts. First, no engine, no matter how clever the design or what kind of fancy fuel it uses, can possibly be more efficient than a reversible Carnot engine running between the same two temperatures. And second, the efficiency of this perfect engine doesn't depend on what's inside it. It doesn't matter if it's air or steam or anything else.
So how do we know this is absolutely true? Through a brilliant thought experiment. Just imagine for a second that you built a super efficient engine that was better than Carnot's. You could use its work to run a Carnot engine backwards, which would basically act like a refrigerator. If you hook them up, this combo would do something impossible. It would suck heat from the cold place and dump it in the hot place, all without any outside energy. It would be like your freezer making your whole kitchen colder. That's a flat-out violation of the second law of thermodynamics. And since that's impossible, our original idea that a more efficient engine could exist has to be wrong. The final and maybe most profound implication of all this is a truly universal relationship. The fact that this maximum efficiency depends only on temperature gives us a way to define temperature itself based on pure thermodynamics, not on how much some liquid expands in a glass tube. It's a universal yardstick for hot and cold, woven into the fabric of the universe. So let's just quickly recap the big ideas. First, reversibility is the secret to getting maximum efficiency. Second, the ideal engine blueprint is the Carnot cycle, 2 isothermal steps and 2 adiabatic steps. Third, the efficiency formula is shockingly simple. It's just 1 minus the cold temperature divided by the hot temperature. And finally, Carnot's theorem proves that this isn't just a theory, it's an unbreakable law of nature. And that leaves us with a final thought. Sadi Carnot basically drew a line in the sand 200 years ago. He told us what's impossible, but in doing so, he gave every engineer a target to aim for. So the question is, how do modern engineers in everything from power plants to jet engines keep chasing that absolute limit, using these principles to squeeze out every last fraction of a % of efficiency?